So, so it's good to see friends in Orange County. I don't know if some of you might know, but I was at UC Irvine for 17 years before I moved up north. So, oh wow, good. So good to see friends and old friends and new friends. So this is a new, hopefully a new topic for people that you do have a lot of problems with as people with epilepsy and even families is dealing with sleep and memory problems. So I may or may not have all the answers for you, but hopefully I will provide some understanding for you to sort of get a deeper meaning from a very basic science side of what happens to people with epilepsy during sleep and why there are memory problems that's associated with it. So not only do I direct the UC Davis epilepsy program, but I'm also a basic science researcher. And so a lot of these information that I'm going to present today are derived from recordings from patients undergoing stereo EEG or SEEG or invasive EEG. You heard of that? SEEG? Okay. All right. So without further ado, so I have no disclosure. So memory problem has been really the cornerstone of a lot of people who are suffering from epilepsy. One of the very first patients that taught us a lot with this patient that was done in 1957. He's known as patient HM, and he was done at the Montreal Neurological Institute. At the time, his seizure was consist of somebody, he was a motor winder, a high school graduate, and he had these major and minor seizures in which the attacks would last about 40 seconds, and then he'll become unresponsive. He'll open and close his mouth, and then he'll cross his arms, and he'll believe that he could half hear what's going on, but actually he couldn't hear. And these were what we now know as impaired focal seizure with impaired awareness, right? But he underwent epilepsy surgery, and after that surgery, there was one striking and totally unexpected problem associated with surgery. He lost all his memories. And what happened in the old days that won't happen again, because we learned from patient HM, was the fact that the surgery involved both sides of the hippocampus. So this is a surgery picture where they took out both sides of the temporal lobe. And the result of that, he lost all of his memories. And that just taught us that the temporal lobe, and especially the hippocampus, is so essential for laying down new memories. So that was the very first patient who kind of happened that. Over the years, we've learned a lot about memory deficits in patients with temporal lobe epilepsy. And this is a study that was published a while ago, looking at the memory of a cohort of patients, but I wish I have a laser pointer. But what you can see is that the blue line on top, across the ages, of the memory performance of people without epilepsy, the controls. And then the bottom line, the middle line, the red line, is our patients with temporal lobe epilepsy. And you can see that there's a lower performance on the memory across the whole age spectrum of patients with temporal lobe epilepsy. So what is the connection between sleep and epilepsy? So this was a study that was actually done by my colleague, Dr. Chidi at UC Davis, and who highlights some of these issues. She's actually a sleep pediatric epileptologist. And in this study, she examined over 600 people, children actually with epilepsy. And what she did was she looked at their sleep scores. And she also looked at the sleep questionnaires and find out how long does it take for people to fall asleep, how long does it take for people to have to stay asleep, have early awakenings, have parasomnias, and so forth. And she was able to classify these patients into groups of minimum, moderate, or severe sleep problems. and you can see versus their sibling controls. And you can see when the bar on my right side goes lower, that means it's below the normal controls. And you can see that across all the cognitive tests, including language, executive function, verbal and memory learning, the people who have severe or moderate or severe sleep problems all have lower performance on this, showing that it might be a connection between sleep and memory and cognitive performance. On the right, it shows that the children, these are kids, their behavior was also worse if they have sleep problems, including what they call internalizing behavior problems such as depression and anxiety, or externally cognitive problems such as aggression and so forth. And so sleep really impacts across the spectrum in patients with epilepsy. And why is that? So in order to answer this question, we'll go back to the very beginning of the question, which is why do we need sleep? Do you ever try to ask that question? It seemed to be a silly question, right? But so why do we need sleep? Anyone? Any idea? Yeah?
Brain function.
What?
Brain function.
Oh, brain function, right. Any other ideas?
Cleaning the cache.
Cleaning the cache. Actually, that is correct. Yes, cleaning the cache. Memory consolidation. That's right.
Immune function as well.
That's right. Okay. So Dr. Tononi a while ago made this proposal. It's called the synaptic homeostasis hypothesis, which is cleaning the cache, your point. And that is that during the day, all the stuff we do, learning, working, keeping busy schedule, it builds up this energy, right? This synaptic cost. It takes a cost in order to do all the things. And we actually, as a result of that, in the brain, on the upper corner right over here, your neurons are actually making these connections. And all these connections sometimes could be a little excessive. And that's why we yawn and we get tired and so forth. So there's this buildup of energy. And the idea is that we need sleep in order to get us recalibrate back to our steady state, clean out the cache. I love that. And so during slow wave sleep, what we see is that there is something called synaptic downscaling. We actually make too many connections, and you can see on the left side down there in the middle of that, near the middle of that circle, from 3 synapses in this picture, it shows that we actually decrease to 2 synapses. So these sort of slowly recalibrating the energy back to its homeostatic level is probably right now the most prominent theory as to why we need sleep. And on the right, it just shows shows that normally this is a histogram of what happens during normal sleep. That you start from awake, you go into when you first fall asleep, what's the first thing you usually do? You dream, right? So that's why you get early into the REM sleep, and then you come out of then you go into the slow wave sleep, and then you go up back to the REM sleep and so forth. You go through many of these cycles throughout your night of sleep, and if these cycles are getting disrupted, then of course this recalibration will be hindered. And on the right, you could see that this sort of homeostatic hypothesis that it's sort of in a simplified way. You can see you're building up the energy during the wake. We have all these synaptic potentiation and so forth, and then this high synaptic density and this energy needs to be recalibrated, and then during overnight sleep, it gets recalibrated, and that's sort of the standing hypothesis. So we started looking at this, and this is the a very recent paper that we just got published in Science Advances on this exact topic. This is a collaboration with my colleagues at Berkeley as well as at University of Tübingen, where they're able to. So we actually are using EEG. You actually can get this energy curve on the left side. This is fancy word is this 1 the power over frequency curve. So the bottom is the high frequency activity. You see go from 10 times per second to 40 times per second, and on the y-axis is the power. And overall you get this energy curve. And what you can see is that the blue is doing awake, and the red is due after a night of sleep when you wake up in the morning. And the energy curve drops overnight. You can see that. So that's really a cool demonstration. How much that energy curve drops between evening and morning is how well your memory you will do your memory test. And that's what showing in B. So we ask people to remember a pair of a word and a nonsense word, like bird and jubu. And then when we train them on bird goes with jubu. Okay? And then we ask them later on to recognize that when we show you a bird, you have to pick between jubu, derf, ufi, and ni. And then if you remember that bird always goes with jubu, then you'll pick jubu. And we do this after somebody wake up. And you can see in C, there's a direct correlation between how much that energy get recalibrated from evening to morning and how much people remember the next day. Showing sort of a direct connection between this recalibration of cashing out system and how you remember. On the other hand, if we took a group of people, and what do we do in D? What does it say up there? Sleep deprivation. So we sleep deprived a bunch of undergrad students. They get extra credit for the class. You can see that after sleep deprivation, what happens? The energy curve didn't really drop that very much, right? The orange and the yellow there was not a lot of difference in the sleep deprivation curve, right? And look what happened to the memory. The memory actually was also worse with the sleep deprivation group. So it shows that so now with EEG we're able to have a signature of this energy curve, and we can see overnight how the brain recalibrates. This is and what from animal work, what we found out is that the most important recalibration is when you go from slow wave sleep, when you don't dream, and REM sleep, and another slow wave sleep, what we call the sandwich. You guys see the sandwich here? Slow wave sleep, REM, dream sleep, slow wave sleep. And from the first slow wave sleep, after you go REM sleep, the next slow wave sleep, the energy curve drops. And that's exactly what happened in D on the bottom, right? You see the energy curve for the earlier slow wave sleep was higher, but then after the sandwich, the energy drops. And that's why dreams are so important, because that's how you really recalibrate, is doing these sandwiches. And again, what we show is that how much that drop between slow wave sleep and REM sleep, and then another slow wave sleep, is when we see the direct correlation with memory as well. So it's not only overall how much of the energy drop, but how many of these sandwiches you're going to have during sleep. That's also very, very important. So how do we form memory, new memory? What happens is that from this very early on hypothesis is that I showed you earlier that patient HM, where they took out both sides of the hippocampus and they can't lay down new memory anymore. So that's why you need the hippocampus. So the information first comes when you see something new or make this pair of these associations such as bird and jubu, that what happens, that goes into the hippocampus. But over time, that information gets transferred into the cortex and lays down. This is why in the hippocampus, we remember things for a very short amount of time, but with a lot of detail. And details are where, when, and how, right? And all those W's. But over time, you remember that while you know, for example, pi is 3.14, but do you remember when you precisely that moment when you learned pi is 3.14? No, right? But the moment that your child learned it, you probably remember, right? It's because that's how the information gets transferred into the cortex, where it becomes more generalized as a knowledge, but you lose the details of the knowledge. So this information transfer from the hippocampus, which is deep inside the brain, to the cortex is essential for understanding of how memory becomes consolidated, like what Russell just told us, that one of the important reasons of sleep is memory consolidation, right? So in order for memory to consolidate, that information has to go from short-term memory to longer-term cortical-based memory. And so what sleep does is that it helps you traffic this kind of memory it's like a traffic control. They're directing the traffic between the hippocampus and the cortex. And the one that directs the traffic are these waves, these very high frequency waves over here called the sharp wave ripples. They occur about 80 times per second. They mainly occur in the hippocampus. And every time they occur in the hippocampus, it allows the information to flow from the hippocampus to the cortex. So these are the traffic directors, okay? And we need those in order to lay down new memory. Well, we only can record these traffic directors. Earlier on I showed you where you can record just from the scalp. But this information, you only can get it if we have electrodes inside. That's why I showed you a picture of a rat, because in animal research, they discovered this traffic director, which is called sharp wave ripple, between the hippocampus and cortex. But only recently have we been able to detect these traffic regulators in the humans, because thanks to the wonderful epilepsy patients that we have that's willing to participate in research, where they have depth electrodes like the one SEEG anyway in the brain, and they said, I consent for you to record me during sleep. And that's what we did. We recorded over probably 10 to 15 patients, all at UC Irvine, actually my former place. And these are all data that came from UC Irvine, where we were able to detect these sharp wave ripples or these traffic directors. And we'll show you what happens. First of all, this sharp wave ripple is very distinct, but when you have an epileptic discharge, so the blue is normal oscillation for the sharp wave ripple. On the right, you can see that spike in the middle of the red line on the right bottom. That's when you have an epileptiform sharp wave. It mimics that sharp wave ripple. It's like the imposter traffic director, and that's what's getting screwed up. Is you have these imposters that look almost like the normal ripple that directs the traffic between the hippocampus and the cortex, but they're not true ones, they're imposters. I'll show you what happens normally when you have these things direct the traffic. So the one on the bottom, and this is a paper that we published in 2021 in the Proceedings of the National Academy of Science. And what we show is that whenever these high frequency activity happens, this sharp wave ripple happens in the hippocampus, is when you have on the right B, is when you have increase in firing of neurons. It goes up like that. So 90% of the time when that sharp wave ripple occurs, the cortex are talking to each other in communication. And that's when the information is getting exchanged. Okay? It's only And then what we found is that the traffic director actually uses the slow waves that you have during sleep to direct the traffic. Because what happens is that if you, let's say, brain A and brain B needs to talk to each other, you get a firing from the hippocampus, and the slow waves in the frontal and the temporal lobe line up exactly in the same phase, so that it opens up that communication channel, so that then the traffic can go through, the memory can be traffic between the two areas. And we find this kind of precise, delicate way of exchanging information that was occurring during sleep for the time. These are all from epilepsy patients, but about 70 to 80% of the time it looks normal, and it is the normal ripple, and this is what happened. We see actually an exchange of information. And in fact, we can predict, this is a prediction graph on the right, we can predict that you could see that the red dot is talking to the white dot, right? And only when these slow waves are exactly in the lining up like your kids at park, they're all lined up precisely, is when these are able to communicate. And we can, the right side just shows that I can actually predict much better than chance, like 70% of the time, when A and B would talk to each other, if we have this precise alignment of the sharp wave ripple, the director of the traffic, with the slow wave doing slow wave sleep. Well, this is what happened during epilepsy. So I show you earlier, so during the epileptic sharp wave, which is here on A and B over here, that red line, you have firing across the whole brain like that, which is the B. We have activity that occurs across all the frequencies, from very low frequency to 120 times a second throughout the whole brain. And that essentially just short circuits that traffic mechanism. So that's the reason why these discharges are so detrimental to laying down new memory. Here's another example. You can see in the middle there's the slow wave, and it is coupled precisely with this ripple activity when this physiological or normal occurrence. You can see on the right, when you have an epileptiform shock wave, there's no pattern to it. It's all random. The neuron discharging all in a random manner, not in a very sort of organized manner as you see on the left side in D. See that? And also, what we found is that when the ripple occurs, the frontal lobe opens up the door and then communicates first with the temporal lobe, and then temporal lobe opens the door about a second later and talk to the frontal lobe. So this bidirectional give and take kind of communication. That's what happens when you have a normal physiology. Well, what happens when you have a pathological ripple? Well, this is the amount of information. So G shows the amount of information that gets exchanged between the frontal lobe and the temporal lobe. And you can see that the gray line on top shows that when this sharp ripple occurs is when this information gets exchanged. So the information goes up. When you have an epileptic sharp ripple or a pathological, which is this brown line on the bottom on the left side, the amount of information actually went down, and then it stays sort of at the baseline. And if you look at on H over here, the amount of information that we exchange, you can see how much less information is exchanged between the frontal lobe and the temporal lobe when you have a pathological ripple versus the physiological ripple. So that's sort of pretty much the end of my talk. I mean, the take-home point is that we need sleep because we need to recalibrate all the exciting things that we do, like coming to Disneyland and all that during the day, and having lots of fun. But somehow, your brain needs to rest, and it's not just rest, but it's really getting that excitability down to a normalized level, and then subsequently, and doing that, if you just open if you have the ability to open the brain and look at what it's doing, it's the hippocampus and the temporal lobe communicating with the cortex that makes the memory lay down or consolidates the memory. And the one that directs the traffic, and I think that you'll impress everyone when you go out there and talk to the doctor and say it's called shockwave ripples. Okay? And those shockwave ripples are the traffic directors, and normally they make sure that first the frontal lobe talks to the temporal lobe, then the temporal lobe talks to the frontal lobe, back and forth. Like, hey, okay, I got it. It's like throwing a football, like catch it and you throw it back, right? Well, when you have an epileptic ripple, it's like the floodgate just get open. And subsequently, because there's just so much neuronal activity in all aspects open up that you can't exchange information. As if we're talking in this room, and I'm trying to talk to somebody down there by the door, but all of you guys are just talking, chatting. There's no way I'm going to be able to get that information across. Well, that's what happens when you have an epileptic spike, is that there's no way for me. And in fact, it mimics that shockwave ripple. That's what's the crazy thing about it. It's a mimicker, an imposter that allows you to stop the information exchange from the frontal lobe to the temporal lobe. So in order, this is why it's, you hear this message over and over again, but this is why it's so important to have seizure controls, because if you reduce these interictal discharges, and people have shown that, then you also will reduce these pathological ripples and improve overnight sleep and hence improve memory. So that's the end of my talk. I'm happy to answer any questions.
Do these ripples, do they manifest themselves during sleep as an actual event?
Yeah.
It does. So,
Yeah.
But like you're woken up because you're having a seizure?
No, you can't feel it.
Okay.
But because we have these probes in the hippocampus,
Right.
we detect them. To me, an event just like a bing, bing, bing. If it was a sound, there's no sound. But but people are able to, like in rats,
Yeah.
they're able to detect it, and they're able to silence it artificially.
Okay.
And so, let's say a rat is able to learn a new maze, and if you silence it, then the next day they don't remember the path of the maze they've gone. So telling us that these ripples actually have like a causal, like it's like if you don't have it, then you can't do it, kind of a thing.
So how long does it take for reducing intracranial epileptic form discharges when you start seeing some improved memory? How long have you noticed that? Does it take a month, a year, 3 years, 4 years, 5 years?
I think that because these things are happening at a very sort of fast time scale, that even faster than that, I think that the less of those, the more ability for them to talk, even overnight, that you'll be able to lay down better memory. Now the problem is that if you can get a steady improvement, that's great, but you get reset back if the seizure get worse. And then all of a sudden, the memory you lay down is sort of erased in a sense, right?
Are there different types of memory consolidation of improvement? Once you get the epileptic form discharges under control, are there different ones that seem to work better than others? Like, say, for instance, learning to round is coming in faster than it is remembering how to spell his last name. And I'm not sure why, but why is it that he can round suddenly, but he can't remember his last name?
Yeah. I think that definitely are things. The things that, what we know is that the things that it's easier to remember if you can anchor it with something else. The human brain is very good at association. So if you put something within context of something, and then you ask somebody to remember, even with, problems associated with epileptic form discharges, they are able to remember those information, because whatever, what's important to humans is what's important sort of individually to us as an individual person. So, what may be important to you as an event you remember, and the emotional aspects that are attached to it is also unique to you. So if you can make it associated with, make it meaningful to that person, it's actually much easier to remember than something that is just a loose association.
But you would think that his last name would mean something or more than rounding.
You may think.
Okay.
Yes, I was wondering, I've had epilepsy for 38 years, and I've always been a slow learner, but I'm curious, can the memory problems also end up with, like, early stages of dementia?
That's a huge debate. And in fact, at the American Epilepsy Society, there's a whole workshop every year on aging and epilepsy. This is not the final answer. My take on this is based on all the research I've done is that no, it shouldn't be. It's the fact that, I'll show you earlier, this actually pertains to this review that Bruce Herman and I wrote in The Lancet back in 2012, specifically talking about, and there's a whole section if you go to find this article called Len Muller Herman Lancet 2012 that speaks to this point. And the point is that that because it's not that people get into dementia, but if you look at the curve for the red, you start at a lower part of the curve, and even though you don't, the epilepsy patient don't fall off the cliff like go really steep, slowly when you drift down, at some point it becomes noticeable for your everyday living. So it's not like people get dementia, it's just that you start at a lower baseline. When you drift down to that critical threshold is when you notice that it impairs your everyday, things that you do. So the answer is no, but we want this line to sort of keep it flat as possible.
I was worrying about, I've been told in medication and so on, they told me to take naps. So a good thing to do is take naps every day.
It's not, if it helps you, then that's fine. I mean, in general, you want to have a very regulated sleep,
Yes.
right? So what I learned from my mother many years ago about, having this habit, not watch TV, not having TV in my room, go to sleep at a certain time, wake up at a certain time. Those goes true for people with or without epilepsy.
Yeah, I think so, because my kindergarten teacher was like, take naps, kid, and it works.
Right. So what you learn in kindergarten still is true.
Yeah.
This is very interesting. Thank you for doing the talk first.
Yeah.
So it seems like what we want to do is reduce the epileptic activity inside the brain to handle better memory. But a lot of us who are actually taking anti-seizure medication are reducing the epileptic activity inside of our brain, but our memory is not necessarily coming back. Is there a trade-off with maybe the medication doing something that we don't know yet, or how does that work?
Well, not that we know that we know that if you don't, and if you have more epileptiform discharge, certainly that impairs your memory. Now, you're right. You not are satisfied with your current memory performance, and you want to do better. And there are ways of sort of keep things stable. I mean, again, the brain is very plastic, and so as much as you can do to improve socialization and to improve, by keeping the brain working. So puzzles are really helpful. Things that are, anything that cognitively challenging is probably a good thing to keep to at least stabilize the memory. And sometimes people even find some improvement in memory. What we also found in some literature is that certain aspects of cognition is transferable. So for example, they've done studies now in school kids where you teach them to have better executive function, which is sort of switch and control. And somehow that could lead to better math performance and academic and memory. So things that we think that it's more of a frontal lobe thing can transfer sometime to areas are not as good. So, you know, the most common form of epilepsy is coming from the temporal lobe. Memory is probably the most common complaint. But there's some weak evidence suggests that, you know, you can't get back what the deficit is. But if you train the rest of the brain, which is very good at other things, to do what it's really good at, such as executive function, switching, and sort of cognitive flexibility, that somehow could transfer to improve overall cognition.
My son started at seizure medicine, and then he started having very intense, vivid nightmares.
Mm-hmm.
If he's having nightmares all night, is that going to give him quality sleep?
Probably not. I mean, that's my guess.
What do you do? I mean, the trade-off still is to control the seizures, but then you're awake, or you're not awake, but you're in the morning, you have all these, you have this terrible activity from nightmares.
Yeah, what I suggest you do is see a sleep specialist and do actually a sleep study.
Do a sleep study.
Because then you can see whether or not he's getting those sandwiches I just talked about. But if he has just intense REM and nightmare and really is not getting it, then you have to think about it. There are certain medications, such as benzodiazepines, that does increase sort of REM aspects of sleep. So it depends on whether somebody's on clobazam or other benzos. Yeah, that's probably the reason why.
What do you do? Take, like, if the clobazam is healthy?
Yeah, that's a hard sort of risk-benefit kind of analysis, right? If you can reduce some of that, but then, you know, have an adjunct with other things, such as, you know, I mean, I think that the combination Epidiolex with clobazam is probably a good combination. Depends. Yeah, like the CBD, yeah. So it depends, you know, I mean, it's hard to say from individual, but I think that while clobazam is good at reducing overall seizures, we know that any benzo has an effect on sort of that sleep architecture that I just told you about earlier.
It could also be sleep apnea.
Yeah.
Yeah.
Yeah, and sleep apnea could be another one, so sleep test definitely is indicated.
And that's what I was going to bring up, actually. I was going to ask you about sleep apnea along with something like this.
Yeah.
What's, you know, I mean, obviously it's going to make it worse, right?
Well, yeah, it's just disruption, but it's also the lack of oxygen, and,
Right.
and so that certainly could make it worse, yeah. Yep.
Somebody that is a recovering drug addict and alcoholic, does seizures and that, is that a direct correlation with you know, me, I do like to, I'm an adventure seeker, skydiver, motorcycle rider.
Mm-hmm.
And getting that, that rush that I get from those activities that I do, does that have a direct correlation with the seizures and my medication and like, you know, replacing drugs and alcohol with, you know, sugary foods or that kind of stuff?
Yeah. I don't think so. I think that everyone's different, and you know, how you derive that joy in a sort of a more beneficial way than a more detrimental way is probably pretty important, and you're doing great. Yeah, but I don't think there's anything wrong with it. I mean, I don't think this is sort of a way of kind of, you know, covering something up. I think that people who enjoy, as long as they do it in a very mindful way, you know, that, you know, that's, you know, the important thing is that this is a thing that you enjoy and you're getting a lot out of it.
Do a sleep home test, is that we've got good to say results?
Yeah, right now most of the sleep tests are home tests. Yeah.
ESES, working on that ESES pattern, I don't know if you know about it, electrical.
Mhm.
Okay.
Mm-hmm.
Have you guys done any studies on any particular cognitive rehabilitation programs or anything like that? Nothing?
Not that I'm aware of, like specifically for, yes. I mean, that's where the sleep is really getting disrupted because, you know, you talk about predominant discharges during sleep, right?
Right.
That's the definition of it. So yeah. So I'm not aware of any rehab as far as I know.
Our daughter also has this, so she has 5 ways regularly during sleep, at 30% considered controlled, so she's having problems forming new memories. In your studies, have you seen a point where it flips over where you see memory loss?
I don't think the study that we do actually would be able to answer that.
Okay.
Yeah. Okay. Oh, we have a question in the back.
Can memories be transported into dreams?
Can memories be transported to dreams? Yes, that's an excellent question. Yeah, there've been studies done where you're trying to tag memories. And animals actually can actually tag their memory. They're called engrams. And then later on, figure out where these cells that have this one precise memory that they form during wakefulness, where did they travel to? And which part of the brain it gets laid down. So in humans, we're really, some people may claim they could do it, but it's not quite there yet. But the wake memory does get transferred in sleep and get modified, and then it gets transferred. So yeah, so great question. It's fascinating actually.
Sleep spindles, can you talk more about those? At the beginning of the illness, there was no sleep spindles, but as treatment continued, there was more sleep spindles. Does that have anything to do with the memory?
Yes. So I kind of skip over the sleep spindles
Okay.
a lot because I just don't have time to talk about every aspect of it.
Right.
But let me see if I can find the. So this is the. So you can see that in this study, you see spindles on the bottom.
Yes.
So the brain goes sort of in this up and down state, and when they have this up state is when you see those little dots on the bottom. Every time when the neuron fires, cells fires. So whenever you have a spindle, is when you have lots of neurons firing, and whenever you have the slow wave is when you're in a down state, is when you don't have a lot of neuron firing. And the brain during sleep needs to switch between this very active and this less active state. And we don't know exactly the reason for these switches, but having spindles is critical. The spindles actually will couple with the slow wave and will couple with the sharp wave ripple, all in sort of this what we call a trifecta. And that's when the best traffic is getting directed, is when those three things all line up exactly the same. So the fact that your son have more spindles after treatment is probably a very good sign. Yeah.
Is it normal not to dream? Or is that a way of not getting deep sleep?
Well, sometimes we just don't remember our dream. It doesn't mean that you don't dream. It's only, we don't remember the dreams that we had when you first fall asleep, although there's an active REM period. You pretty much only remember the ones you just waking up, or somebody just woke you up in the middle of your REM sleep. So it's probably, it's not possible for you not to dream, basically. Because unless, if you lesion the gene that causes REM sleep, the animals die, essentially. So it's not a physiological condition.
Because I have not been able to sleep at night. I wake up every hour. I don't even watch TV before I go to bed. How would you say to control that, to get more into it?
I think that first of all, it's a very difficult problem, and it's not something that you can solve sort of on a daily. The interesting thing is that the more you think about sleep and worry about sleep, the less you're gonna sleep. That'll be my. People, it's such a counterintuitive thing, but if you fixate on sleep, then you're not gonna sleep. And so the key is to just really having that switch off mechanism at night as much as you can, rather than worry about it. In the beginning, it's a very painful process, right? Because you really want to go to sleep, but you can't fall asleep, but then you worry about sleep, and at the end you'll find, just give up. And the way to really do it is to, over time, just realize whatever sleep I get, I'm grateful for it. I start on the next day, I'm going to start fresh, and it's a new night, and I'm not going to worry about it. That's probably the best advice somebody has given me, personally.
So even though, like you said,
Well, certainly sleep deprivation makes the seizure worse, right? We've known that for a long time. But the point is that worrying also causes more anxiety and problems too. At the end of the day, there are certain mechanisms that we are inherent, and such as a circadian rhythm and sleep pressure. So like I show you that homeostasis process. Eventually, everybody sleeps. Okay, it's just being human. And there's also that circadian clock that allows you with the melatonin and all of the stuff that allow your body to fall asleep. The problem is that when you start messing with that clock, first it works great. Like you take a couple melatonins, boom, 12 hours sleep, the best night you ever had, right? You do that every single day for 30 days, it doesn't work anymore, right? That's the thing, is that you can't mess with the physiological clock. And to me, I know it's easy to say, but if I'm taking care of a lot of patients' sleep and have my own share, I could tell you that even the best of drugs will mess you up. That it is really understanding that everyone sleeps, and it's okay if you don't sleep one of these nights, and tomorrow is another night, tonight is another night. Don't ever had thing happen before, doesn't really matter, right? You have a new day, new night, and go on with it. That's probably the best advice. And remember, everybody sleeps.
Yeah.
Okay, thank you very much.